Hey everyone, today we're going to continue to work with sampling distributions, and the activity is called What was the real average for the last chapter test? Okay, so we still are sticking with the same theme as our last activity. How did the Unit 4 test go? We're still going to be taking a sample from a population, but now we're going to use the average sample to estimate the average for the population. Okay, so in our last activity, we looked at a very small class of students as our population. Remember, there was only 4 students in the class. In reality, there's many more people that are in the class. So what we want to do is we want to take a random sample of 5 students and record their scores. Then we're going to find the mean, and we're going to repeat this for a total of 4 times. Okay, so here are all, if you go to the very last page, all of the actual test scores. So we're going to assume I had 50 students. I numbered each number 1 through 50. So like this one is the first student, second student, third student, fourth student, all the way down to the 50th student. And here are all the scores they got. So if we were all in class together, what I would have you guys do is I would have each person take 4 random samples of size 5. So you would use on your calculator randint 1, 50, and you'd randomly choose 5 test scores. So for example, you could get 75, 75, 85, 91, and 81. And that would be your sample of 5. Now, and then we would repeat that process 4 times. So if we did that as a class, we would all end up with different samples of size 5. Now, we're not all together in class. You guys are at home right now. So just kind of follow along with me as we do this, and then I'll show you what a dot plot would look like if we did it in class together. Okay, so let's just say you randomly chose 5 scores, and they ended up being this: 72, 89, 74, 91, and 85. And then how about 78, 63, 100, 72, and 52. Then you took another sample of size 5, so we got 76, 83, 85, 70, and 40. And then our last sample of size 5 is 85, 91, 74, 87, and 93. And keep in mind, if you were doing this legitimately, you would want to ignore repeats because each of these numbers represents one student. So for example, if I select this student that had a 72, I wouldn't want to select the same student that had a 72. You could select a different student that had a 72, but not the same one. So we would ignore repeats. Okay, so I have 4 different samples of size 5. So what I want to do is, out of these 5 students, what was their average, or what was their mean? So we know we can do that just by adding these together and then dividing by 5. So I'll just show you real quickly what those come out to be. So the mean for these first 5 scores is 82.2. The mean for our next group of 5 students is 73. The mean for our third group of students is 71. And the mean for our fourth group of students is 86. Okay, so we really just found 4 statistics. These are all the sample means of all the students in the class, and notice that none of them are the same. Now, they could be the same, but by chance they are not the same. Okay, so what we would do in a normal year is every single student in the class would have 4 different sample means, and I'd have you guys come up to the board and you'd stick your stickers where your sample means were. Okay, so since we're not together, I actually did this myself. I randomly chose 30 different samples of size 5 the other day, and these are the results I got. Okay, so it's always important to have a good understanding too, and we'll get to this in a second, of what each one of these dots represents. So for example, remember this 68 is not one student that scored a 68, but this 68 is a group of 5 students where the mean of those 5 scores is a 68. Or this is 5 students whose mean score or average score is an 86. So each dot represents a sample of 5 students. So this is not a population distribution. This is a sampling distribution of X bar. Now I'm actually going to take it even a step further. I'm going to call it a simulated sampling distribution of X bar. Okay, which I know you guys don't have this dot plot on your paper. So what I would do at this point is I would pause the video and just copy in this dot plot. Okay, and like I said, keep in mind each one of these dots is an X bar. Every single dot in this dot plot is a sample mean of size 5. So you guys get the point there. And then number 2 asks us kind of what we already answered. It says, what does each dot on the poster represent? Well, we just said that. Each dot represents a random sample of 5 students and the mean test score calculated for that sample. And the mean test score calculated for that sample. Okay. So what do you think the true Unit 4 test average is? Well, we did have one sample that said the average was 68. So do we think the population average is 68? Probably not, because that was only one sample. So what we want to do is we kind of want to figure out what's the average of all these different samples, or basically where's the middle of your graph. If I had to guess, I would say, heck, it looks like maybe 79 might split all this data in half evenly. So I'm going to say about 79, I would guess, because it looks like half my samples fall below 79, half my samples fall above 79. Okay, number 4 says a sampling distribution shows the means calculated from all of the possible samples of size 5 from the population. Is the above dot plot a sampling distribution? So does this graph show all possible samples of size 5? Well, no, we only have, I think, 30 dots here. So this isn't a true sampling distribution. That's kind of why I said it was a simulated or an estimation of a sampling distribution. So it's really important that we know that a true sampling distribution does all possible samples of that size. And I'll actually calculate how many there should be, how many samples of size 5 there could be, to show you how large or how many dots that would be in a second. So we're going to say no, this is not a true sampling distribution because we didn't take all possible samples of size 5. Okay, look at how many there would be. If we have 50 things and we're choosing 5 of them, how many different ways can that be done? And I'm saying 50 because remember there were 50 test scores and we're choosing 5. So if we put in our calculator 50 choose 5, it actually ends up being over 2 million. It's kind of crazy to think about that there's that many different combinations of 50 samples of size of 50 things or samples of size 5, I guess I'm trying to say. Okay, so yeah, this is definitely not a true sampling distribution. There's not 2 million dots here. So number 5, we took a random sample of 5 midterm scores at Keystone Oaks High School and got a mean of 68. Is this convincing evidence that KO students did worse than students at our school, or is it possible that KO students had the same average? Okay, so what we want to do is we want to go up to our sampling distribution and locate where 68 is. And we want to see how often did we end up with a sample of 68 or less by chance. And why are we saying or less? Because we're asking, did the KO students do worse? If we said did better, then we'd look at 68 or higher. Okay, so coming up here, there's only one sample of size 5 that is at 68 or less. Okay, one sample out of, I told you there were 30 dots here. How likely is that to happen by chance? An average score of 68 or less would be 1 out of 30, which is 3%. Okay, so our students, just 3% of the time by chance, are going to end up with a sample mean of 68 or less. This is a very low number. This is statistically significant, meaning it probably didn't just happen by chance, the Keystone Oaks students. So this is convincing evidence. When that percent is below 5%, that means yes, there is convincing evidence. This didn't just happen randomly. So let's put that into words. Yes. If KO had the same average as our school, it would be very unlikely and we're getting that number from 1 out of 30, which is equal to 3%, to get a sample mean of 68 or lower. Okay, remember, this 3% means that this 68 happened for a reason. It didn't just happen randomly. This 68 probably happened because they just did worse on this test. Before we move on to the check your understanding, because it really finishes up the activity, I want to just go back up to number 3 and tell you, so we guessed just by looking at our simulated sampling distribution of X bar, we guessed about 79. So if you would take all 50 of these scores and average them, the average score actually comes out to be 80. Okay, so our population mean is equal to 80, and what we guessed, 79 and 80. Now, keep in mind, we just guessed. We could take the mean of all these and figure out what it is, and I would assume it would probably be very, very close to 80. Remember, that means that X bar is an unbiased estimator. We talked about that in our last activity. It's unbiased because the mean of the sampling distribution is equal to the population mean. Okay, so before you turn this video off, let's take a quick look at the flip chart notes. So the flip chart notes we should be looking at are sampling distributions day 2. So there's not a lot on here. It's just kind of talking about what we did in this activity. So we can use the sampling distribution of a statistic, in this case it was X bar, to evaluate a claim about a parameter, which was mu. We were trying to figure out something about the population mean. So when we evaluate a claim, the first thing you always want to do is assume that the claim is true. Okay, then we want to create a simulated sampling distribution, which is what we did by taking all of those random samples of size 5. Then find the probability of getting our observed result by chance alone, which in this case we were using that KO score of 68 as our observed result. Okay, so for example, we look at the graph, we take the observed result or more extreme, could be greater. In our example, it was less than. And we see how often does that happen by chance by taking, for example, here 2 dots divided by the total number of dots. And then here's how we interpret. If that percentage is less than 5, like it was in our activity, then we do have convincing evidence against the claim. Our results occurred for a reason. In our activity, the reason was KO did worse. If the percentage of dots is greater than or equal to 5%, then we don't have convincing evidence against the claim. So if that would have happened in our activity, we would have said, you know what, KO probably didn't do worse than us. We just got that sample mean by chance. Okay, so I would like you guys to take what we just talked about here and go through the back on the flip chart notes, check your answer key on Canvas, and then come back to the activity and finish the check your understanding.